All right, let's get straight to it. Today, we're breaking down a serious, no-limits engineering plan. And the objective? It's one of the most audacious things ever conceived: to drill a continuous, open tunnel straight through the entire planet Earth. This is the mission briefing. So, what does success even look like for a project this insane? Well, the definition is brutally simple and just unbelievably difficult. We're not just digging a deep hole here. The goal is a perfect, uninterrupted shaft, over 12,000 kilometers long, so clear that you could shine a laser in one side and see it come out the other. Think about that. This isn't about exploration. This is about the complete conquest of geology.
So where do you even start with something on this scale? You can't just pick a spot and start digging. The very first phase is all about defining the mission parameters. What exactly are we building? And critically, where on Earth do we break ground? This decision alone sets the stage for the entire 40-year mission.
Let's be really clear about the scale we're talking about. This isn't a pinprick. We're planning for a borehole with about a 10-meter diameter. Now, for perspective, the deepest hole ever drilled, the Kola Super Deep borehole, was only about 9 inches wide at the bottom. This is a highway through the planet, engineered to stay open permanently and resist being crushed by unimaginable forces. Okay, so choosing where to start is a huge strategic decision. It's a game of trade-offs. The primary choice is the southwestern U.S. Why? Well, the crust is relatively thin, which is a great head start. The catch? The geothermal gradient is high, meaning things get incredibly hot really fast. The backup plan is Hawaii. It's got the thinnest crust on the planet. We're talking just 5 or 6 kilometers deep. But you'd be drilling straight into an active magma zone. Yeah, tricky. The other backup, the eastern U.S., is cooler, more stable rock. Sounds good, right? But the crust is much thicker, so it's a brute force approach that means drilling through an extra 10 to 15 kilometers of rock. When you weigh it all, the Southwest offers the best balance of risk versus reward. All right, locations picked. Now the first great challenge begins: punching through the Earth's crust. And this isn't a one-and-done kind of deal. It starts with raw mechanical power, but eventually, as the conditions get crazier, the strategy has to shift to something straight out of science fiction. The whole strategy for getting through the planet is really split into two completely different philosophies. For the first 30 kilometers or so, it's all about brute force. We're talking proven, heavy-duty mechanical rigs that physically chew and grind their way through the rock. But you go deep enough and that just stops working. The rock gets superheated, it gets almost plastic. So the mission has to pivot. It transitions to thermal and energy-based methods. We're talking about using directed energy to literally melt or vaporize the path forward. It's a fundamental shift from force to fire. So this is what that first brute force phase looks like. Think of it as traditional drilling, but just scaled up to an absolutely superhuman level. You've got massive drill bits made of tungsten and diamond alloys, driven by hundreds of tons of downward force to just pulverize the rock. A special circulating fluid is constantly pumping down to flush all that debris back up to the surface, and to keep things moving, the drill bits are replaced by a robotic system, and a segmented steel casing is fed in right behind it, reinforcing the tunnel walls as we go deeper. And this is the turning point. At around 30 kilometers down, the game completely changes. The heat and pressure becomes so intense that the rock doesn't really act like rock anymore. It's so hot and ductile that it would wrap around a mechanical drill bit and destroy it in seconds. Conventional technology hits a hard wall. Brute force is officially off the table. It's time to get radical. So, what's the radical new method? Meet gyrotron drilling. Instead of cutting the rock, you're going to boil it. A gyrotron creates this incredibly powerful, focused millimeter wave beam. It's basically a super industrial microwave that literally vaporizes the rock in front of it. Then a high-pressure blast of argon gas comes in and just blows all the vapor and molten junk out of the way. And this isn't just theory. This tech is being developed right now for things like geothermal energy. For this mission, though, it would be scaled up to become an industrial weapon aimed at the planet itself. Okay, so we've blasted our way through the crust. But honestly, that was the easy part. Now we enter the next great frontier, the Earth's mantle. This is a journey of thousands of kilometers through a region where the very physics of rock changes. And it presents a challenge that makes everything before it look, straightforward. This quote from the scientists who worked on the Kola Super Deep borehole. It just perfectly captures how alien this environment is. Under that much heat and pressure, rock stops being a brittle solid that you can drill through.
It flows, it deforms, it behaves like a thick plastic. You can't drill a hole in it in the normal sense. It would just squeeze back in and seal the tunnel right behind you. So to fight this plastic rock, the mission calls for an entire arsenal of extreme technologies. We're talking about things like laser spallation, which uses an intense laser to rapidly flake off layers of rock, and as a bonus, it creates a self-sealing glass lining along the tunnel walls. You've got plasma jet drills. You even have plans for miniature nuclear reactors built right into the drill head to just melt everything in its path. And for the really tough spots, controlled nuclear or chemical explosions to shatter huge volumes of rock ahead of the drill.
And if dealing with plastic rock wasn't enough, you're eventually going to run into pockets of pure magma. As this slide makes terrifyingly clear, that's an incredibly dangerous problem. The Krafla testbed in Iceland is a perfect and horrifying warning. A drill there accidentally hit magma, and when they tried to cool it with water, the result was a steam explosion so massive it was catastrophic. So yeah, a new approach for dealing with liquid rock is absolutely non-negotiable. And this is that new strategy. It's actually an ingenious multi-step process. First, a device they call a freezing sock is sent down ahead of the drill. This thing injects a cryogenic fluid, we're talking liquid nitrogen, all around the magma pocket, flash freezing a shell of it into solid obsidian. The drill then just bores right through that temporary frozen plug. Any leftover liquid magma is then carefully rerouted into parallel high-pressure pipes, getting it safely away from the main borehole. It's a brilliant piece of engineering. We've made it through the crust and the mantle. Now we begin the final descent into the most extreme environment on, or maybe I should say in, our planet. This is the final frontier, the Earth's molten outer core and its solid inner core.
Just look at this chart. It shows you the staggering leap in temperature. The lower mantle is already a blistering 4,000 degrees Celsius. But as soon as we hit the outer core, that jumps to 5,000 degrees. That's as hot as the surface of the sun. Down here, materials don't just melt. They stop behaving in ways we can even comprehend. And then there's the pressure. 330 gigapascals. That's more than 3 million times the air pressure you're feeling right now. It is a force so immense it can crush any material known to man, literally forcing atoms into weird new structures. This pressure, this is the single greatest enemy of the entire mission. So how on earth do you drill through a literal ocean of molten iron under that kind of pressure? Well, you use a brilliant and completely counterintuitive strategy. Instead of trying to fight the molten metal, you use it. You lower a prefabricated steel liner down into the liquid core. Then you flood the borehole with a dense cryogenic fluid. This instantly freezes a layer of the liquid core directly onto the liner, basically welding it into place and creating a solid, self-made iron sleeve. You turn the problem into the solution. The final push is through the solid iron inner core. And at this point, it's not about finesse. It's a pure battle of attrition. The environment here is so hostile that the survival time for any piece of equipment is measured in hours, maybe even minutes. The assault continues with the most powerful tools in the arsenal, the nuclear and laser drills. But the strategy is just one of constant replacement. Liners, drill heads, reactor modules, they're all treated as consumables, constantly being swapped out as they are literally consumed by the heart of the Earth. So, after conquering the crust, the mantle, and the core, after actually emerging on the other side of the planet, what's the final bill? What is the accounting for this monumental feat? Well, the resources required are, to put it mildly, astronomical. First, let's talk about time. The total estimated time to complete this is 40 years. 40. That's not just a project, that's a multi-generational endeavor. Many of the people who start this mission will not be there to see it finished. Next up, energy. The total power needed is estimated at 1.7 times 10 to the 20th joules. It's a number so huge it's almost meaningless. It's tens of billions of megawatt hours. You would need entire arrays of dedicated nuclear power plants running 24/7 for decades just to power this one single project. And finally, the cost. The estimated total price tag for this mission comes in at around 40 trillion US dollars. That one single project would cost more than anything ever built in human history, combined. It represents a commitment of global resources on a scale we've never even imagined. So the plan is laid out. The challenges, as immense as they are, all have engineered solutions, at least on paper. But it really leaves us with this one last question. If we could actually do it, If we could marshal the resources and the political will to bore a hole clean through our world, what would that really signify? Would it be the ultimate triumph of human ingenuity, or would it be the ultimate folly? What does it truly mean to conquer the very ground beneath our feet?